Welcome back. Now we have learned transfer function. We want to apply transfer function to more complex problems. In this video, I will walk through an example on technique. Now let's get into the example. Given constant liquid density ρ, volume V, and mass flow rates of W1 and W2, we have individual one. And the big W is total flow rate. And we have the governing one here. And X are the composition, and the big X is the total composition, is the output, and have varying input of X1, while X2 is held constant. So we have identified our constant, input, output, and the governing. So we're given the original ODE. We want to find the deviation ODE. And recall that the deviation is equal to original minus steady state. So we want to find the steady state. The steady state, all time variation goes to 0, so at the left is 0. And on the right, we write out everything. And then note that the input and output will be at steady state. So the output X will have a bar, and the input X1 will also have a bar. And then we minus original ODE to steady state ODE, we have rho V dx dt minus 0 equals to W1 X1 minus X1 bar plus W2 X2 minus X2. That is just 0. And minus W minus X. And then substitute for the definition of deviation variable W1 X1 prime W X prime. And on the left, we use dx prime dt, solve for the definition, is x minus x bar, and bar is a constant. So we use dx dt. So dx dt equals to dx prime dt. Substitute that in. We have our deviation ODE. Notice that our deviation ODE is different from the original ODE because the W2 X2 term is constant. That does not show up. So we cannot simply just add primes to everything. That does not work. We need to derive that. Now we have found the deviation ODE. Find the transfer function, we take the Laplace transform of both sides. Left we have rho v are constant, and the Laplace transform of the derivative x big X prime minus initial condition equals to W1 the constant and Laplace transform of x1 prime and minus constant Laplace transform of x. And note that we can use the initial condition. The deviation variable we assume initially steady state deviation is 0. This goes to 0. And because we want to find the transfer function g, which is the output divided by the input, and our output is x, input is x1, so we want to isolate big X plus W big X equals to W1 prime of X. And then we rearrange the equation so that big X is at the top and X1 is at the bottom. So we have W1 divided by rho V plus. And then to write it in more general term, k divided by tau s plus 1. We want to multiply top and bottom by 1 over w. At the top we have w1 over w divided by rho v divided by w as 1 equals to k tau of s, where k is defined as w1 over w and tau is defined as rho v w. And now we have derived our transfer function. Either use this one, or we can also use their equivalent. Let's look at a similar example, but this time we have x2 is also an input along with x1, so it's no longer a constant, and we still have output of x and the same governing. So given the original ODE, want to find the deviation ODE, need to find the steady state ODE. Steady state time variation goes to 0. Write out the right hand side. And we put all the output and input to steady state values, so we add a bar to that. And then original minus steady state equals to deviation, rho v dx dt minus 0 equals w1 x1 minus x1 bar plus w2 x2 minus x2 bar minus w x minus bar. Then use the definition of deviation variable. We can rewrite. And again, we can write it in terms of the derivative as deviation variable and use the definition of it to get left hand side. Dx dt is equal to dx prime. And now we have our governing ODE in the deviation space. And note that this time there is very similar form with the original ODE because we don't have a constant term. Okay, now we have the deviation ODE. We can find the transfer function by taking the Laplace transform on both sides. Rho v Laplace transform of derivative s x prime of s minus initial condition equals to 1 big X1 w2 big X2 minus w, and the big X's are a function of s. And then again we invoke the initial condition of deviation variable 0 at steady state. X prime of 0 equals. And this time we have the output of x prime and then the input of x1 prime and x2 prime. So let's solve for the output. Rho vs x prime of s equals a plus wx prime from the right hand side, and then copy. And then isolate big X, w1 x1 prime, w2 x prime, and on the left we have the coefficients rho v s plus. And this can be rewritten so that we have common form of something tau s plus 1 on the bottom. So to do that, we will multiply the top and bottom by 1 over w. That will give us W1 over W1 is W2 over W divided by rho V W S plus. And then since it is division, we can separate the top terms, still have the same denominator. So the first term is W1 over Wx1 prime plus second term W2 Wx2 prime. This is equal to x. Why do we write it this way? So that we can write it in terms of k, standard form. So we have k1 1 prime divided by tau 1 plus 1, k2 x1 x2 prime divided by tau 2s, where in this case we have sine k1 as w1 over w2, k2 is w2 over w, excuse me, k1 is w1 over w. Tau 1 is the same as tau 2, which are rho v divided. Now if we look at this, we cannot write it in terms of transfer function yet, but we need to impose some new condition on it. Now we want to impose some condition on the output Laplace transform. If the effect of x2 of t is 0, and the only thing in effect is x1 of t, that is not equal to 0, then in the Laplace space, its deviation variable is 0 for 2 and non-zero for 1. So we can have prime of s equals to, the first term survives because it is non-zero, but the second term, x2 prime 1, goes to 0, so that goes away. We can write it in terms of transfer function. So the output divided by the input x1, that gives us the transfer function, is equal to k1 divided by tau 1s. Similarly, if we impose that the effect x1 of t 0, the effect of 2 is non-zero, then its deviation variable in the Laplace space, first one is 0 and the second one is non-zero. So that we can write it in terms, first term goes to 0 as 0, the second term survives. Again, we can write it in terms of transfer function of output divided by the input. That's the transfer function 2. Find that. Goes to k2 divided by tau 2 plus 1. So now we have found the transfer function x1 and x2. Then we can substitute them in. So that gives us g1 of s, big x1 prime, plus g2 of s, x2 prime of s. And this is a very interesting form. Why do I say it is interesting? I have two comments. First one is that we can see it is linear. The first term is the effect of x1 of t on the output x of t. The second term is the effect of x2 of t on the output x of t. And they are linearly additive. So if we have a third effect, I can add on the third effect, 3 of s, x3 prime of s. And that's why transfer functions are so easy to use. They are linearly additive. The second thing is that if we consider that all other effects goes to 0 and only consider one effect, say we only have the first effect, then we see that we have output here, we have input here, and this is the transfer function. So you can think of it as transfer function acts on the input, which gives the output. So transfer function maps the input-output relationship. In the Laplace space, or the S space. And it's so great to use because it is linear. So in this video, we went over an example to show transfer function of multivariable ODE. And we found that final result shown linearity and reveals input-output relationship in the Laplace space.